All right, Maxie, be good. Good morning, guys. Welcome back to MAC 1140 section OR1. Sorry for the little delay here. My puppy and kitty are having a bit of an interaction, so I may need to try to save her from him in a moment here. We'll see. But today we're going to begin talking about chapter 2. We're going to start talking about functions. So the kitty's running away up here. See here. And we're going to take a look at some of the problems of the sort that you're going to see on your next homework set. Oh, don't be a terrorist. Alrighty, so let me go ahead and flip over to the doc cam. We can get started properly. I want to remind you that starting this week, you have 2 homework sets due per week. So there is a homework set that opened this morning, which is going to be due for you at the start of class on Wednesday. And then on Wednesday, there will be another homework set that opens up, which will be due the following Monday. So this is MAC 1140. Section OR1, that's a pre-calculus class, and today is the 30th of August, 2021. Today we're going to go over sections 2.1, which is just on sort of the definition of a function, and section 2.2. Which is on graphs of functions. So I think most of this is material that you guys will have seen before. Again, we're going to move kind of quickly, but we'll also be thinking about it a little bit more deeply than maybe you did in previous algebra classes. Just that reminder. Homework 1 was, of course, due at the start of class today. Like right now. Homework 2 is due at the start of class on Wednesday. And then homework 3 will open Wednesday and be due at the start of class the following Monday. So we talked about this last week. This is kind of a regular thing. The first week we made an exception, just having the 1 homework set because we needed to give time for people to come in and get settled. But now everybody is settled. The add drop period is over. So we should all be kind of getting into this routine of having homework, making sure we get the homework done before each class day. So at the start of every class day, you're going to have homework due, just like today. If you didn't get homework 1 done to your satisfaction, remember you can always just come in here and submit an extension request and I will grant them. So just in WebAssign, I think once you get into the homework assignment, somewhere on the top or maybe on the very bottom, there's an option to request an extension, and I will pretty much always grant those. I granted the ones that were in there this morning when I went in. But this is what your next homework set looks like. And I want to say just one thing about the homework set before we dive into the material today, and that is, as you solve these problems, the graphing problems especially, right? Graphing these piecewise functions or these sort of problems, you need to make sure that you're drawing the graphs by hand, right? I know it's a little bit tedious to come in here and draw the graphs by hand, but you need to do it. Just like guessing among the 4 graphs until you get it right is not going to teach you anything. So please, please, as you do the homework, draw the graphs by hand.
I have a question.
Sure. Oh, I think you went back to mute, sorry.
When will the homework that opens on Wednesday be due if we don't have class on Monday?
It's a good question. Probably the next class day. Probably the next Wednesday then. All right. So let's get to it. Oh, maybe one other little thing before we go. if you look in the modules, I have some resources that I want to point out as being useful for this particular homework set. So if you follow this Desmos link, it has all the basic graphs that you should know. By the end of this week, you need to know what all of these graphs look like. Okay, and there's nothing hugely difficult about this. These are all things that you've seen before in other algebra classes, but I've got them broken up into different families here. They're all just power functions. So these are positive integer power functions. And if you want to look at the x to the 4 graph, just click the little circle over here, it'll show up. If you want to look at one of these root graphs, like the 4th root or 5th root graph, just click the little circle here, it will show up. And then these negative power functions, reciprocal functions, absolute value functions. These are what we call parent functions. These are kind of basic graphs that you want to know, because in the next few sections, we're going to start shifting these around, stretching them out, flipping them over, all sorts of things like that. So knowing these, having this library of parent functions clear in your mind is going to be very, very important for the lesson on Wednesday. Many of them are things that you'll practice graphing in this homework set. I just wanted to show you what that's there. Okay, so let's do it. I don't want to patronize anybody, but what is a function? Anybody want to explain to me? Or just tell me in your experience, when you think of the word function, what comes to mind? No wrong answers.
Is it like a relationship with one variable or in another variable, like two variables in it?
Yeah, I like Jean-Baptiste's answer there. It's definitely a relation. That's a key word. So we can define a function in terms of the word relation, which in mathematics has a very specific meaning also. And then something about some number of variables. So I'm going to say it kind of intuitively like this. A function is a rule which relates inputs, which would be represented by one variable, to outputs. And we can be a little bit more specific here. Specifically, a function takes each input and pairs it to one and just one output. Okay, so that's basically the idea. And you can think of the inputs as being represented by a certain variable, usually x. You can think of the output as being represented by some other variables, often y. Although we're going to try and get a little bit more comfy with the f of x notation, the function notation in this class, because there are some advantages to the function notation over calling the outputs y. So Jean-Baptiste's answer is really good. A function is a relation or a rule that relates inputs to outputs. So you can think of this kind of pictorially. You know, you've got some collection of stuff over here, and you've got some other collection of stuff over here. Usually these would be sets of numbers. And function is a rule which tells you how to take a given thing from the input space and map it over to something in the output space. So if I call the function f, then the particular output associated with the input x, I call f of x like this. So the function is f. The set of inputs over here, this is called the domain. Just like when we talked about domains of expressions, we can talk about domains of functions, and it's all the things that you can plug in, which is, you know, the set of all the inputs. And over here you have the set of all the outputs. which is called the range. And kind of the big thing that I need you guys to get comfy with in this section isn't really anything technical. It's just how to interpret this notation, the function notation. So f is like the machine, x is the input. You can think of these parentheses as kind of being like a mouth. So f has this mouth that it uses to eat these inputs, and then it poops out something. So you can think of f as a digestive system, or a machine that eats things and spits things out, if you like. The set of all inputs is called the domain. The set of all outputs is called the range. That's the basic terminology. The only sort of subtle technicality here is that every input needs to go to one and only one output. It's not immediately obvious when we get started with this that this is a restriction, but it actually is a pretty heavy restriction on the types of things which are functions. When we talk about graphs, we'll see some tricks to help you recognize whether or not a given relation is or is not a function. But I'll say just again, when it comes to figuring out whether something is a function or not, the question you need to ask yourself is, does every input go to one and only one output? So maybe before I run off to talk about notation, should just look at a quick little example of how this can go wrong. This means, like, it is not possible for f of 3 to be 5 and f of 3 to be 7, because there's one input. The input 3 needs to go to only one output. Right. So for example, if I told you f of 3 is equal to 5, that's how we read this statement. That means that f takes the input 3 and pairs it with the output 5. And if I simultaneously told you that f of 3 is equal to 7, that would mean f takes the input 3 and sends it or pairs it to the output 7. Well, 5 and 7 are different dudes, and 3 is one dude. So I would have the one input 3 getting sent to the two different outputs 5 and 7, and that violates this, right, which is the definition of a function. So that's the sort of thing we don't want to have happen. And the idea behind this rule is that you can infer just from looking at the input kind of where you are, either on the graph or in terms of a table or something like that. The statement f of 3 should carry every bit as much information as the output being listed explicitly. This is all well and good, but it doesn't really help us understand how to work with the things. So the next little bit I'm going to do is just a bit of practice with function notation, doing some calculations. Are there any questions about the picture here or definitions? Okay. So one of the things that we have to gatekeep in this class, right? Because the next class after this is calculus, and calculus, we're dealing with functions all the time. One of the things I really have to gatekeep in this class is a comprehension of function notation. If you don't come to understand what f of x plus 5 or f of x minus h stand for, then you're not really ready to move on beyond this class. So let's pay careful attention as we compute a bunch of things. Let's do f of 0, f of 3, f of 1/2, f of h, f of a squared, f of x plus h, and f of 1 over a, where f of x is the function that, let's keep things simple for now. About x squared plus 1. So I've got this big list of things I want to compute. Each one of these things up here is an output. Each one of the things in this list is an output for the function f that's listed here. So again, if I want to refer to the function is just f. F of x, this is like a formula that tells you how to get a particular output from a particular input. So oftentimes we'll see functions described this way as formulas, like algebraically. There are other ways to describe a function too. We'll talk about that in just a second. But first, I just want to see if we can compute these different outputs given the algebra rule for the function f explicitly. Oh, Nalakat's going to visit us. Hey, kitty. You're very cute. I know you don't like the puppy. Can't be up here right now, baby. I'm sorry. Okay. So let's do it. If I ask you to compute f of something, then you just plug that thing in for x. So f of 0 is what you get by swapping the x in this formula for 0. That's the 0 squared plus 1. And then, there's some amount of arithmetic to do here. So like 0 squared is 0, 0 plus 1 is 0. I'm sorry, 0 squared is 0, 0 plus 1 is 1. So this guy is 1. If I want f of 3, that means I look at this formula for f of x and I just swap the x for a 3. You'll see me doing this in parentheses. That's a really good habit to get into, especially when you get to these slightly more complicated things. So anytime you plug into a function, at least in your very first line, use some parens where you're plugging in. 3 squared is 9, 9 plus 1 is 10. F of 1/2, this is going to require that I do a little bit of fraction arithmetic. F of anything is that thing squared plus 1, so this is going to be 1/2 squared plus 1. I may need an extra step or two to simplify this. 1/2 squared is 1/2 times 1/2, which is 1 times 1 over 2 times 2, that's 1 over 4. So this is 1/4 plus 1, and I'm not really happy until I have that as a single fraction. So I can think of 1 as 4 over 4, and then this is 1 over 4 plus 4 over 4, which is 5 over 4. So plugging a number into a function, nothing too crazy, right? You just plug that number in there, and then make sure you follow your order of operations as you simplify. These latter things here, we're plugging other symbols in. But the good news is you have this algebraic rule that tells you exactly what f does to any input. So f of dog shit would be dog shit squared plus 1, right? F of a soccer ball would be soccer ball squared plus 1. I don't know what it means to square a soccer ball or to square dog shit, but symbolically I can definitely write it down because I have the rule here. So we just kind of follow the rule. I don't know what h is. H could represent anything. H might be another function. H could be a number. H could be any one of a mess of things. But f of anything is that thing squared plus 1. So f of h is h squared plus 1. All right, and if I'm being careful here, I should put this in parentheses. But then we notice, oh, okay, h squared here. There's nothing, the parentheses is a little bit redundant. The order of operations rule would say that's the same as h squared plus 1 like this. F of a squared is what I was asked for next. So everywhere I see an x in this formula, I'm just going to swap it for parentheses a squared. So I have a squared squared plus 1. And the square of a squared, that's a squared times a squared. And you remember you can use that rule for exponents that we learned last week. When you raise a power to a power, you multiply the powers. So this would be a to the 4 plus 1. And f of x plus h this is one that can give folks some trouble, but you just follow the same exact thing, right? Whatever is inside the parentheses here, you want to replace x with that, and you want to do so in parens. So this is parentheses x plus h squared plus 1, like this. Pause on this one just for a second, because there are some things we can compare this to. This is not the same as f of x plus h like this, which would be this, or f of x plus f of h, which should be oops. So f of x plus h, this is again where people do tend to get into a little bit of trouble when you've got more than one piece. Kind of you've got some addition separating the pieces that you're plugging in. Your input is represented as a sum. You need to be very careful about, again, plugging in using parentheses and not confusing that for one of these. I see a lot of people doing things like this when asked for things like this. So remember, just follow the definition of the function. Don't try to do anything fancy. I wouldn't want to undersell the importance of understanding expressions like this, and how readily we can confuse them for things like this. So the plus h is happening on the inside, which means it's a part of the input, which means you just need to replace in parentheses the x or whatever your independent variable is in your formula for the function with whatever is inside the parentheses here. We could clean this up a little bit if we wanted. We could FOIL that out. This would be x squared plus 2xh plus h squared plus 1. And in some contexts, that would be useful. Like if I was trying to simplify a big expression that happened to involve this piece, writing it out like this would be nice. Okay, last one, f of 1 over a. It's going to be 1 over a quantity squared plus 1. And this is kind of similar to the f of 1/2. If I want to square 1 over a, that's going to be 1 over a times 1 over a, which is 1 over a squared. And the plus 1 is still just plus 1. And I could have a common denominator here too. I can think of this as a squared over a squared. And this is 1 over a squared. So this would be 1 plus a squared over a squared if I chose to have a common denominator. Okay, I'll give you a second. Make sure you've got all these nice and clean in your notes. If you have any questions, especially about these latter few ones, don't hesitate to ask. And while you do that, I'm gonna hide my dog from the cat. Maxwell, hey, I love you, puppy. I do. But you're crazy. Crazy rat. Yes, you are. Let's hang out with that, okay? You gotta be nicer to the kitties. All right, any questions about this?
I have a quick question.
Yeah, what's up?
The x plus h, when you, on that second line, where did you get that 2 from?
So I'm foiling this out. So this piece and this stuff are the same. And that's coming from just a quick foiling that I did in my head. So if we look at x plus h squared, that's x plus h times x plus h. And then if you do the normal FOIL thing, your firsts are x squared. Your outers are x times h. Your inners are also x times h. And then your lasts are h times h, which is h squared. So that gets us the x squared plus 2xh plus h squared.
That makes more sense. Okay, thank you.
Yeah, no problem. Is there anything else that we'd like to look at a little more carefully here? Okay. Okay. I did want to make just a slightly more general comment. In general, and in math, the word in general means like the way you should think about it most of the time. Meaning, in general here, I'll say f of x plus h is not equal to f of x plus f of h, nor equal to f of x plus h, or anything like that. I know it might seem like I'm being a bit redundant with this, but I really want to make clear f of anything in this case would be that anything squared plus 1, or whatever your formula gives you. Whatever your function's formula says. Just take the thing that's here and plug it into the formula for the function. And you want to do so in parentheses. There is no other correct way of interpreting statements like this. Be tempting, but I don't want to do that. Okay, I want to do one more of these that has us working a little bit more carefully with some fractions. We'll move through a bit quicker. You can get used to working with different symbols. Let's compute h of 0, h of 2, h of a plus 1, h of, I'll do x plus h again, h of 1 a squared this time, where t be 1 over t minus 2. So again, this function, you've been given an explicit formula, an algebra formula for the output. Says that the function h takes whatever you feed it as its input. It's going to subtract 2 from that thing and then divide 1 by that thing. So if I wanted to describe this function in a verbal way, I would say this is the function that takes its input, subtracts 2, and then takes the reciprocal of that. All right. H of 0. Well, my variable here is t, but that doesn't matter. The same thing is true, right? I just take my variable and replace it by whatever the input is specified here. So h of 0 is 1 over, I'll write it with the parentheses, 0 minus 2. That's 1 over -2, or -1/2. H of 2. This is going to be 1 over parentheses 2 minus 2, which is 1 over 0. What's going on here?
You can't have a 0 in the denominator.
Yeah, that's right. So if I wanted to talk about the domain of this function, just like we talked about last week, you'd find the domain of this expression. You see that the bottom's not allowed to be 0, which means t, my variable, is not allowed to be equal to 2. So this, which leads to this, is a problem. We would say this is undefined. And then a little comment here, t equals 2 is not in the domain of this function, h. All right, in fact, we could find the domain. It's all real numbers except for 2. H of a plus 1. Well, let me ask a question. So, is this equal to 1 over a minus 2 plus 1? Do me a favor, don't write this down, just help me out. Or is this 1 over a minus 2 plus 1 over 1 minus 2? Or is this something else? What do we think? We're looking for h of a plus 1. My function h of t is h of t equals 1 over t minus 2. Is this first guy correct? Yes, it's not this guy. I saw a couple of head shakes. This guy would be h of a plus 1, which is not what we want, right? We want h of parentheses a plus 1, single thing. What about the second guy? I see a little more head shaking. It's not this guy either. This would be h of a plus h of 1, right? This is what you get if you plug in a to this formula. This is what you get if you plug in 1 to this formula, but h of a plus h of 1 is not the same as h of a plus 1. So it is something else. What is the something else? Well, I'm going to take my formula for h, and then in place of the t, I'm going to write parentheses a plus 1. So it's this. And that we can clean up a little bit. A plus 1 in parentheses without a power or anything. I can just ditch the parentheses in my next step. And a plus 1 minus 2, that's a minus 1. So this is the reciprocal of a minus 1. So there are other ways to describe functions. First, any questions on this stuff? These first ones? Okay, let's look at h of x plus h. Ooh, this is a little bit misleading, isn't it? It's this h here. Let me use a lowercase h or something, and they're all lowercase. Here's a script h for the inside here. So I've done something naughty, which is use the same letter to represent two different things, right? So the h inside here is not meant to be the same as the function h. So I'm just going to use a little script h. But we get the idea by now. The idea is just you take the formula for your function, plug in whatever is in here in parentheses. So this would be x plus little script h minus 2. Which we can just write as the reciprocal of x plus little script h minus 2. And then h of 1 over a squared. Get a little bit more practice with our fractions here. So it would be 1 over parentheses 1 over a squared minus 2, like this. We'll clean this up, and this will be the last of these things that we do. All right, who can tell me how to simplify this? Bottom expression here. How can I get a step closer to having this as a single fraction?
Could you reverse it like with the last one where you just did 1 over a plus 1 over a?
Something like that, yeah. So what I need is a common denominator, right? I've got so remember, fractions always kind of imply parentheses, top and bottom. So I've got a 1 upstairs, and then I've got this difference of two things downstairs, one of which is a fraction. And this 2 doesn't have the same denominator as this 1 over a squared. So like in the last one where I had to treat 1 as a over a, here I need to do something similar. I need to have a common denominator down there. So I'll leave my 1 over a squared alone. And then the 2 I'm going to write as 2a squared over a squared. And then remember, always thinking of the bottom as being in a big paren. So the little parentheses around the 1 over a squared, I can stop writing that because it's not being raised to any power. There's no number out front that I need to multiply through. I'm going to leave the big parentheses just to remind us what the groups are, right? Big fraction bars always imply big parentheses. And then in order to clean this up downstairs, I'm subtracting two fractions. Anytime I want to add or subtract fractions, I have to have the same denominator. So how do I write 2 as a fraction with denominator a squared? Well, you multiply by a squared over a squared. So 2 over 1 times a squared over a squared, that's 2a squared over a squared. Are there any questions about how I get this from this? All right, we're almost to the good stuff. Now that that bottom has been rewritten with a common denominator, I can do that subtraction. So this would be 1 minus 2a squared over a squared. That's my denominator there. And again, the parentheses are important here, especially at this stage where you've got like two long fraction bars and it's really easy to confuse what's the numerator, what's the denominator. I think putting the big parens around the downstairs is a really good idea. again, I want to make sure we're all comfy here. Are there any questions about how we got this bar bottom right thing? Okay, if we're all feeling good and confident, who can tell me the last step? How do I finish simplifying this? We're almost done. This whole thing here.
I think you would multiply 1 times the reciprocal of the lower one.
Yeah, what Henry said is perfect. So this is 1 divided by a big fraction. So to clean that up, I'll treat that as 1 times the reciprocal of that big fraction. So how do you know which piece to flip? Well, you got to look for the outermost fraction and find the downstairs of that. That's the thing you're going to flip. So really what I'm thinking of here is the numerator is like 1 over 1, and this is like 1 over 1 times the flipped version of that denominator. But of course, multiplying by 1, you just get a squared over 1 minus 2a squared. So this would be our final answer for that last piece. All right, so I'll say it one more time just to be clear. I will absolutely be gatekeeping function notation in this class. It's one of those things that like can't really move on until you get this. Gotta get this 100% comfy. We're going to be using it all semester long. I will couch certain problems in terms of function notation, and you need to be really comfy with it. But having said that, there are other ways of describing functions. So what I've been doing here, where I give you the formula for the output in terms of the input, like this right here, is called an algebraic description of a function. The other ways we can describe them algebraically, that means I give you formula for the output. They can also be described verbally. They can be described with a table or chart. And they can be described as a graph. So a little bit of practice with the verbal description thing, because this is going to be kind of useful when we talk about inverses. You'll get practice with graphs and tables and charts when we talk about the section on graphing. So verbal description. Let's practice one from the algebra of the verbal. Give a verbal description with words of the function f of x equals x plus 1 squared minus 3 over 7. All right, so this is the algebraic description. It's just a formula for the output in terms of the input. I'd like to get a verbal description. You got to think about your order of operations to do this. So I've got some parentheses, some exponents, some multiplication, division, and some subtraction. Remember again, the fraction bar implies parentheses. So this is really something we think of like this. But you don't usually see people writing those outer parens. So if I plug a number x in here, the first thing you're going to do to it is add 1. So first add 1 to x. Okay. Then square that. So that's the x plus 1 right here, add 1 to x, then you square that number, then subtract 3. And lastly, divide the result by 7. Okay, so not anything amazing. This would be a verbal description of that function. It might seem silly, but it's good practice. It helps with the order of operations stuff in your head to kind of run through this. And later when we talk about inverse functions, you'll see that the function we can cook up which exactly undoes this guy is going to undo each of these steps, but in reverse order. So you want to get comfy with describing these things verbally, so you can describe their inverses verbally, and that will be how we sort of discover function inverses. We could go the other way. I could ask us to give the algebraic description of the function g, which has verbal description say first divide x by 4, then cube that, then and 5, and finally take the square root of that. So I've been given a verbal description. This new function here, g takes x and divides it by 4, then cubes the result of that division, then adds 5 to that, and then at the very end takes the square root of all that. So you kind of start with the inside, right? Divide x by 4. Okay, that's x over 4. Then cube that. So, okay, I'm going to take x over 4 and cube all of that. Then we're going to add 5. Okay, so I take that whole thing and I add 5 to that. And finally, we're going to take the square root. So I'm going to take this whole thing and shove it under a square root. This would be g of x. Are there any questions about how to go back and forth from the verbal to algebraic description? Or algebraic to verbal? Okay. So I want to talk a little bit now about piecewise defined functions. These are something that here at Santa Fe we don't cover in college algebra, so for a lot of folks this will be their first time seeing it. Just to introduce. oftentimes, especially when we're thinking about a real world situation, we're trying to describe a function that does something that we understand kind of in our minds, but we don't see the algebra for right away. It's useful to describe those things piecewise. What a piecewise function is this? You'll see something like f of x equals, and then curly braces. And then you'll have a few different formulas. And then a specified domain. So I'll say it like this, range of x values, a piece of your domain. And then maybe some other formula, if, and then some other range of x values. This is generally how these things look, and I'll show you an explicit example in just a minute. But the basic idea is if you want to figure out f of some particular number, you first match up which one of these range of x values that number falls into. Once you've found that, you plug that x value into the appropriate formula. So, simple example first. This is actually a famous one. I'll call it capital H of x. It's called the Heaviside function, named after Oliver Heaviside. This is 0 if x is less than 0, and it's 1 if x is greater than or equal to 0. This is a piecewise constant function. It kind of has two different behaviors. It behaves like the constant function 0 for all the x's which are negative, and it behaves like the constant function 1 for all of the x's which are non-negative. Let's compute h of -2, h of -1/3, h of 0, h of 1, h of So remember what I said? In order to plug something into a piecewise function, first you see where the thing you're trying to plug in lies. Does it lie in this first range of x values or the second range of x values? So when I go to compute h of -2, well, is -2 less than 0, or is -2 greater than or equal to 0?
Less than 0.
Certainly less than 0, right? So h of -2, it's either going to be 0 or 1. These two numbers, these are the only possible outputs for the function h. And since -2, the number I'm plugging in, is less than 0, we're going to get 0. Okay, what about h of -1/3? I want to plug -1/3 in for x here. In order to do that, to figure out what output I get, I have to figure out whether I'm in this range of x values or this range in x values. Okay, so what is h of -1/3 and why?
Zero because it's a negative.
Very good. H of -1/3, the output when I plug -1/3 into this function is going to be 0, because -1/3, the x value I'm plugging in is negative, less than 0. Okay. Next one we wanted was h of 0 itself. What is h of 0? Plugging 0.
1.
Very good. H of 0 is 1. So 0, the x value I'm plugging in now, is this guy, right? It's greater than or equal to 0. That x value satisfies this range of x values. So the output here is 1. H of 1. Well, I want to plug 1 in here. I ask, is 1 less than 0? No. Is 1 greater than or equal to 0? Yeah. So the output will be this guy. and h of pi. What is h of pi?
One.
That's also 1.
Very good. This is also 1. So again, this function is only ever capable of spitting out two numbers. It either spits out a 0 or a 1. It'll spit out a 0 if you feed it something which is negative. It'll spit out a 1 if you feed it something which is not negative. Again, this guy is called the Heaviside step function. And this is maybe a good time to start talking about graphs. Let me go ahead and graph this for you. We haven't defined what a graph is yet explicitly. I'll do that for you in just a second. But this Heaviside step function is an important function from differential equations. So I will just draw the graph for you here because we haven't really practiced this together. The point I just plotted is 0, 1, right? On the x-axis, I went over 0, and then on the y-axis, I went up 1. If -1 is here, -2 is here, and we computed h of -2, we know that's 0. We computed h of -1/3, which would be like right here. We computed h of 1. We saw h of 1 was 1, so that would give me another point up here. Computed h of pi. Pi would be like somewhere over here. So here's a few points that are on the graph of this function, and the whole graph looks like this. There's an open circle here. We'll think about that in just a minute. And then the rest of the graph is actually down here. So you can see why we call this the step function. It starts out at 0 and it stays there until you cross over 0, and then it steps up 1. It's useful as an input when signal processing, that sort of thing. All right, a little bit more practice with calculating outputs from piecewise functions. Then I'll formally define what a graph is, and we can look at graphs. Okay. The same sort of thing. Let's compute. Sure, why not? C of 0.5, C of 2, C of 4, where the function C of x is piecewise defined as the constant 39 if 0 is less than or equal to x is less than or equal to 2, and 39 plus 15 times x minus 2 if x is strictly larger than 2. Okay, so again, piecewise function. I've got the curly brace. I've got kind of two different formulas, and then each formula has an associated collection of x values. So if I plug something in that's between 0 and 2, I use this formula. If I plug something in that's bigger than 2, I use this formula. All right, what is C of 0.5?
It's 39.
Very good, it's 39 because 0.5 is between 0 and 2. I would use this first formula, and again, this first formula, this is just a constant function. That's 39. C of 2. What is this?
Would it not be
39.
39 also?
Good, very good. This is 39 also because 2 is a part of this collection of x values, right? 2 does satisfy this. So again, this is 39. and C of 4. That's going to come from this guy, right? Because 4 is bigger than 2. So let's just plug it in, write it down. This is going to be 39 plus 15 times, I'm plugging in 4 here, so this is 4 minus 2, which is 39 plus 15 times 4 minus 2 is 2. That's 39 plus 30, which is 69. One more little thing before I move on to graphs, and that's a definition of net change. So the net change in a function f from x equals a to x equals b is, just by definition, f of b minus f of a. Net change is what it sounds like. It's how much did the output change as the input goes through some change. So my input here is going from A to B, and I want to know how much did the output change as the input went from A to B. Well, you just subtract the outputs. So for example, with the function above, find the net change in the function C, call it C of x above, that's x goes from to x equals 2 to x equals 4. So this isn't anything mind-blowing. From x equals a to x equals b, the net change is f of b minus f of a. So from x equals 2 to x equals 4, the net change in the function c is c of the big guy minus c of the little guy. That's all. So c of 4, we computed that was 69 minus c of 2, we computed that also, that was 39. So how much did the output change as the input went from 4 to 2? That's what we mean by net change. That's by definition C of 4 minus C of 2, which is 69 minus 39. How much did it change? It changed by 30. So if this function C was measuring something like cost, maybe the insides here are like hours spent on your cell phone or something, the old cell phone plans, then how much does the cost of your cell phone plan go up as you go from talking for 2 hours to talking for 4 hours? Well, that cost goes up by 30. That's the net change. It's just the change in the output.
I have a question.
Yeah.
I couldn't exactly read your handwriting, but what did that say be after above?
Oh, as.
Oh,
This is as x goes from, yeah, sorry, that is a little bit scribbly, isn't it? Yeah, above as x goes from x equals 2 to x equals 4.
okay, thank you.
Yeah, of course. All right. So, graphs. Talk a little bit about graphs. This is section 2.2, graphs of functions. And I know you've all seen graphs since probably like 7th grade, so I don't want to waste your time too much, but by definition, the graph of a function f is the set of all ordered pairs of the form x comma f of x as x runs through the domain. Of f. So a graph is sort of a two-dimensional object. It lives in the plane. It's a collection of ordered pairs. Every ordered pair is of the form something, comma, f of that same thing. So if, let's see. Yeah, let's do it like this. If 3 comma -7 is on the graph of f, what is f of 3? Might seem like a silly question, but you'd be surprised. The only reason I'm doing this example is to remind you that this is always f of this. So who can tell me what this is? Don't think too hard. What's this answer to this example? If 3 comma -7 is on the graph, then what is f of 3?
-7.
Yeah, -7. So this is always f this. Okay. Okay. So I've drawn a graph for us here. I'd like to ask a few questions. Let's find f of 0, f of 2, and f of 5. And let's ask, is the net change from x equals 2 to x equals 5 positive, negative, 0? All right, so a simple little graph with two little questions. What is f of 0?
4.
Very good, right? So the ordered pair, A comma B, or whatever, is on the graph of f of x, means f of A is B. So right up here, you see the ordered pair, 0 comma 4. That's this ordered pair right here. We've gone over 0 and up 4. That means f of 0 is 4. All right, what is f of 2? Well, I should look to the ordered pair associated with x equals 2. It's at the same height, right? This is 2 comma 4. So what's f of 2?
4.
Also 4. Okay, what is f of 5?
Two.
Very good, that's 2, right? So over here, I've got the ordered pair 5 comma 2. So those are the 3 function values I was asked to find. F of 0, f of 4, sorry, f of 0, f of 2, and f of 5. All right, let's look at the net change from x equals 2 to x equals 5. We could actually find that net change, right? I know that's f of 5 minus f of 2. By definition, remember the net change from x equals a to x equals b, the thing that's being asked about here, this is f of b minus f of a. So that's f of 5 minus f of 2 right here. What is f of 5? Well, we just said f of 5 is 2. And then from that, we subtract f of 2, which we said is 4. And 2 minus 4, that's negative 2. So what's the answer to part B?
Negative.
Negative, right? This is definitely negative. We were actually able to compute it. It's exactly negative 2, which is negative. All right, I'd like to ask a follow-up question. Same as part B. But from, I'll do 2 little sub pieces here. Let's do from x equals 0 to x equals 2. And then from x equals 1 to x equals 4. So I want to know, is the net change positive or negative? First, let's look from x equals 0 to x equals 2. Well, in this case, I can do the computation again, right? I know exactly what f of 0 is, and I know exactly what f of 2 is. So this one here, f of 2 minus f of 0 is what? What's f of 2?
4.
And f of 0?
4.
Okay, so the net change here is 4 minus 4, which is 0. Now, what do you notice? Before we try to answer this last little piece here, the net change from 2 to 5 was negative. The net change from 0 to 2 was 0. Can anybody parse that for me in terms of the picture here? Why was the net change from 2 to 5 negative? We're looking from here to here. What is it about the graph that could have told me without doing the computation that the net change from here to here would have been negative?
There was a reduction in your Y value.
Yeah, overall, from 2 to 5, I went down. This point is lower than this point. So if your B comma F of B point is lower than your A comma F of A point, then overall your output has decreased, gone down, which means your net change is going to be negative. Right? If I say the net change in my account over the last month is negative, that means that I ended up with less money than I started with, gone down overall. So the fact that this point is below this point could have told me that the net change from 2 to 5 is negative. Let's try to understand the 0 to 2 net change in that same way. How could I have known that this is going to come out to 0? Their heights are the same, right? They're both at Y value 4. So if you end up in the same place you started, like if my bank account is exactly the same at the end of the month as it was when it started, then my net change is 0. So being along the same horizontal line, having those points at the same height means that that net change is going to be 0. And having the larger point, the later point below the starting point tells me that my net change is going to be negative. So now let's look at the x equals 1 to x equals 4, because I don't know what f of 1 is, and I don't know what f of 4 is. But can you tell me whether that net change is going to be positive or negative?
Negative.
Good, it's definitely going to be negative. Right here I have the point 1 comma f of 1. I don't know what f of 1 is. It looks like it's a little bigger than 4. Over here I have the point 4 comma f of 4. I don't know what f of 4 is, but it looks like it's somewhere between 4 and 2. So because from here to here I've gone down, I know this will be negative. So if overall you go down, your net change is negative. If overall you go up, your net change is positive. And if you end up at the same height you started at, your net change is 0. That's going to be an important intuition for us a little later. Let's see how we're doing on time. I think I am out of time here, right? Yeah, you guys are 8 to 9:15. So we're going to stop here for the day. One last thing though, again, before we go, please take a look at these graphs of parent functions in Desmos. These guys will help you out. There's a link right here. And then get started on this homework. You've got everything you need to do this homework. Let's see, this one. This is you. So you're just going to graph a few functions by plotting points. You're going to get practice making tables and graphing functions. Some of them are piecewise functions. Some of them are defined verbally. I don't think you'll have a hard time with any of this, except maybe the piecewise function stuff. And I want to say again, this is due at the start of class on Wednesday. All right, so it's a fair amount of homework. I think there's something like 40 questions here. You need to get started on this today. All right. I don't think you'll find any of it too hard. If you're stuck with anything, you can come by office hours or send me a Canvas message. You can use the Ask My Instructor function in WebAssign, but I'll say this, I don't check that stuff anywhere near as often as I check my email, Canvas messages, and Discord. There's just too many ways to reach out for help. So the Ask My Instructor, it's clunky. You have to type mathematics. It's a pain in the ass. By far the best way to ask for help is to send me a Canvas message or post to the Discord. But that's it. Please get started on that homework. You've got plenty to do between now and Wednesday. Let's do at the start of class on Wednesday when we will pick it up and start talking about ways to combine and play with functions. All right. Any questions for me before I let you guys go? All righty then. I will see you guys on Wednesday. Take care.